All right, so this question talks about work. And again, there are two ways of thinking about work, either in terms of a force and a displacement, or looking at how the energy of the system is changing. In this case, they're asking us for a force. And so we would begin with this version of the work formula. And again, you might want to rearrange it, do the algebra first, and see that the force would be the work divided by displacement. And then that would come out to be 180 newtons. Again, if you put standard units into a formula, you get standard units out. This problem asks us to sort of think about work the other way in terms of that work changes something's energy. In this case, the problem is talking about changes in speed. And so this would be a case where we'd want to think about the change in energy as being a change in kinetic energy, meaning that we'd want to subtract a final value, k, minus an initial value, k sub 0. Some people like to use k sub f and k sub I for final and initial. That's fine, use whatever symbols make the most sense to you. In this case, because the boat starts from rest, that initial kinetic energy is actually 0. So basically, the amount of work we were given in the beginning of the problem, 5,400 joules, is the final value of kinetic energy. So now we should be able to determine the speed. Again, we'll grab our kinetic energy formula. We can either plug things in, or I'm going to rearrange to find V first, practice my algebra here a little bit. So I would multiply both sides by 2, divide by m, and then square root to find the speed. Again, standard units in, standard units out, so this would be 5.2 meters per second when I do my algebra. All right, let's take a look at this work problem. So in this case, again, I could think about this in terms of forces and distances, or I could think about it in terms of the type of energy that's changing. And that's how I'm going to approach this. Since the position is changing, that means the potential energy is changing. And so I'm going to think about this as work equals change in potential energy, meaning that I would want to subtract the final potential minus the initial. The formula for gravitational potential energy is m times g times y, where y is the vertical height above some lowest point. There are a couple of ways that you can approach this question, but a common way is to just assume the ground is the 0 point and to measure all of your heights relative to that. So there would be an initial potential energy of 9 times 10. Remember, 10 comes from the gravitational field strength on Earth. So 9 times 10 times the initial height, which is 0.5. And then to repeat that calculation, just using 1.7 as the height instead. So these are our two values of y. And then to find the change in potential energy, we just subtract the values. And that determines our work. So that comes out to be 108. By the way, another approach would be to first subtract the heights and then just do the potential energy calculation once. But this is a more, I don't know, let's say it's a safer way of doing it, because sometimes it works to do that subtraction first and sometimes it doesn't. And so this is the way that will always work for you. Now, if this process requires 1.5 seconds, we can determine how much power was needed. Power is the rate at which energy is being transferred. So in this case, we can just think about this as work over time, since we've already calculated the work. So that's the 108 joules divided by 1.5 seconds. And a joule per second is stated as watts. Now, officially, the abbreviation for watts is a capital W. But because capital W is also a symbol in our formulas, I like to write the word watts out. That way, there's lots of confusion as to which W I'm talking about. Entirely a preference, but that is something, a habit I've gotten into to avoid making silly mistakes like thinking work and watts are interchangeable. The other unit for power is the horsepower. So let's just take a quick look at what this value would be in horsepower in case maybe you're familiar with those sorts of numbers. 1 horsepower is 746 watts. And so we can set up a conversion so that the units are set up diagonal from each other and see that this is a pretty small amount of horsepower. Usually things done by a human are. You really need some sort of engine for it to be a significant amount of horsepower. So just a quick summary that delta E or W can be found in a couple of different ways. Sometimes we're just going to use the formula that most people think about when they think about work, force times displacement. But you don't always have that kind of information in a problem. Sometimes you're given information about the speed of an object before and after something happens. Sometimes you're given information about the height of an object before and something happens. So if the problem is talking about lifting and you're given information about the change in position, then you may end up wanting to do it this way. You might end up looking at the change in gravitational potential energy. Note too, though, that since mg together is the weight of the object, and that's how much force you would need to lift it, some people actually do think about these lifting problems using this formula as a force times a displacement. There's kind of two ways of looking at it. But if you do have a situation where the object's speed is changing, you really have no choice. You have to think about what the final kinetic energy is, what the initial kinetic energy is. Again, here I'm showing it with F for final and an I for initial because some people prefer that. Some people just like to use V and V sub O. Okay, so it's kind of just a preference as to what makes more sense to you. But it is important to notice that you can't just subtract the values of V. Because they're squared in the formula, you really have to take the time to calculate individual values and find that change in kinetic energy. But however it is that you have found the work or the delta E, if you're asked to find power, you take that value over time. And that will tell you the rate at which energy is being transferred. So this idea of work, we now know how to calculate it if we know a force, but why would we even need to do this in the first place? Well, it only really comes into play when there's some sort of external force acting on the object, again, the three ways of representing that force, and then friction is part of the system. Then this is how we're going to incorporate that. So if there's an applied force, and many times that force helps the object's motion, and so the work is a positive amount, and so our final energy ends up being greater than our initial energy. So looking down here, whatever our initial amount, we would be adding something. This would be positive. And so this final amount would end up being a greater value than what we started with, instead of being equal. If there's work being done that's negative, meaning the force works against the motion, friction would be a great example of that, then all that changes about our setup is that the W, the work value, is negative. And so then your initial value would be bigger than your final value. But by just kind of adding in this plus W to the left side of your setup, you are good to go in terms of incorporating work into your setup. Another way to represent this is to say that work represents the change in energy and some people do prefer to do that, but it does require you to make sure that your signs are all perfect and everything. I like this method here because it builds off of what we've already been doing in terms of energy. So to approach this question, what I want to look at is how much energy this box has right now stored in it, moving at 2 meters per second. So that's going to be its initial kinetic energy. And then I want to try to figure out what its final kinetic energy is going to be, so I can figure out the speed at that point. But what's different, because it's not the same amount of energy, is that the force is doing work. And so it's adding energy to that initial kinetic energy. So I need to calculate some different values here and sort of put it all together. To find the initial kinetic energy, I need to figure out how much mass it has. Obviously that's given to me as that 5 kilograms. I need to know what speed it has to start with. So maybe the initial speed, v sub o, v sub I, v sub 1, something like that. And then I need to figure out how much energy is going to be given to the object, because there's a force acting on it. And that, of course, is what we call work. So recall that work is calculated by looking at how much force is being applied, how far the object moves, and what's the angle between those two things. Because if the force is not completely with the object's motion, then it's not completely effective in transferring energy to the object. So that's how we calculate work. And then that should tell me how much energy I have at the end. And this energy is again being stored as kinetic energy. It's going to be more kinetic energy, a new value. Call it final F, final V. All right, so what we know here then is that my initial kinetic energy is 1/2 times 5 times 2 squared. Could calculate what that is. It ends up being about 10 joules. And then I have a force of 20 newtons being applied as the object moves 1.3 meters. But again, those are not in the same direction, so I need to use an angle here. Now, the angle that I was given is 35 degrees, but that's the angle between up and my force. My object isn't moving up. My object is moving to the right. It's being pulled to the right. So this is the angle that I need. That's where the cosine of that angle is going to tell me how much force is pushing with the motion. So I'm going to use the cosine of 55 in my setup. All right, and that together comes out to be, I think, about 15 joules. That's right. I don't remember that number off the top of my head here. Let me quick check it. Yeah, 15 joules, actually about 14.9, but about 15 joules. And then that will equal 1/2 times my mass times my new speed that I'm trying to find squared. So that's going to equal 2.5 times my speed squared. So if I go through and solve this equation, I started with 10 joules. I added 15 because there was work done, so that I have 25 joules of energy. And so then that determines what my speed is going to be, or what my kinetic energy is going to be. And then I can go ahead and calculate what the speed is, making sure that I take the square root of my answer and so forth. So I get about 3.16 as that speed. All right, so let's look at the next step of what might happen and look at energy being taken away from the system as well. All right, so here we have that same block, the 5 kilogram block, but it's moving at this 3.16 that we just found, and it reaches this rough spot of the ground, of the table. And so it's going to start to slow down. Energy is going to be redistributed. It's going to be taken from the kinetic energy, and it's going to go into thermal energy. It's going to heat up the block and the surface, the table. And so
floor. And so what we want to do is figure out, well, how long is it going to take? How far does the object move before all of that energy has changed from the kinetic energy that it now has to thermal energy where we can't get it back? And so we can set this up very formally, again, same way we did before, and say that the object has now some kinetic energy based on that 3.16 meters per second, and there's work being done, and so there's final kinetic energy. So the same idea of how work changes the amount of energy the object has. So we would again say 1/2 times our mass times our initial velocity squared, but now our initial velocity is this value because we're changing which part of the motion we're looking at. And now our work is going to be specifically the force of friction that's working against the motion. And we're going to have a change in x that we're going to try to find. This is going to be our question mark. This is the thing we're looking for, how far the object slides. And then watch carefully here. Our angle is actually 180 degrees. Okay, because the object is moving to the right, that's our delta x direction, but the force of friction is pointing to the left. So there's 180 degrees between those. What that's going to do is introduce a -1 to our setup so that the work is negative. The work is the energy being taken from the object instead of being given to the object. And in the end, the whole thing comes to a stop. And so there's no speed, there's no energy stored anymore as kinetic energy, and so this should all end up being 0. All the energies switch to the thermal energy. All right, let's remind ourselves of how to calculate friction. Look back at your formula sheet and so forth if you need to. Recall that that is mu times our normal force. And in this case, our normal force pointing up would exactly balance our gravitational force pointing down because there's no motion vertically here. So our gravitational force would be 5 times 10 newtons per kilogram, so 50 newtons. So that's going to also be our normal force. So 1/2 times 5 times the speed at the start of this section plus mu 0.25 times the normal force. Okay, so this thing all together is our force. And then I don't know how far it's moving, that's my displacement. And then we have the cosine of 180, which is -1. Okay, so we can go through and work out this whole problem. So this, actually we had done it before, so this is 25-ish, 0.25 times 50 times -1. We could put all that together is about 12.5. And so we would bring one of those over to the other side and divide by 12.5. We get a distance of about 2 meters that this object would slide.